Hello and welcome. In this video, we'll be discussing the chi-squared goodness of fit test, which is a second type of chi-square test that we can do with categorical variables. So, as I just said, this is the second type of chi-square test we can do with categorical variables. And in this one, instead of comparing two categorical variables to one another, we'll compare a distribution to the categorical variable. For instance, I might want to see if the counts match some pre-specified distribution. This could be based on the budget or size of a department, and I want to see if the department's return on investment matches the percentage of investment of my total investment that I'm putting into the department. I might look to see, are the counts evenly dispersed across categories? I think that we're getting the same number of sales from each department or something like that, and I could compare or build a distribution based on that called a uniform distribution. Uniform distribution just says everybody is the same, and see if my counts match that. Or anything else. I mean, another one we had is the normal distribution, where essentially I make quantiles based on a normal distribution and build in categories for that. So for these, the test statistic, degrees of freedom, and critical value are calculated the exact same as they were for the test of independence. So the test statistic is still the observed minus the expected squared divided by the expected, and add up all of those. The degrees of freedom is the rows minus 1 times the columns minus 1, kind of, but now we don't have rows anymore. So this is just going to be the number of columns minus 1. That's going to be my degrees of freedom. And the critical value is still going to be calculated from the chi-squared. So mathematically, the test of independence and the goodness of fit test are the same. What changes is how I get the expected values. So in the goodness of fit test, or in the previous test of independence, I had to like do the row times the column totals divided by the total number of things, etc. In the goodness of fit test, I simply find the counts for each of the cells using those pre-specified input things. So the pre-specified counts might come in counts, but often they come in percentages. So for instance, if I'm comparing the sale of 3 products and I assume that all 3 sell equally well, I might have the percentage sales in each product be, say, 33%, 33%, and 33%. From there, what I would do if I were given percentages for each product or bin is I would then take those percentages, put them in decimal form, and multiply them by the grand total sample size. And that would give me my expected count within each cell. So for a second example, with 4 groups, if I were looking at the uniform distribution, that is, I assume all 4 groups are going to get the same counts in each, I would take the 100% total distribution divided by 4, and I would expect that there would be about 25% in each group. To find the expected count, I would take the decimal version, 0.25, and multiply that by the total number of observations. All right, well, let's look at some marketing allocation. Business has been investing and marketing with a new product, our new AI, the Hokey Opinionated Robot, or Thor for short, because you know what? I get to write these lecture slides, so I get to put Thor in them. The business has been pursuing 3 different marketing campaigns, digital, paper, and mass marketing, but these have differential costs. The cost for the digital campaign is $150,000 per year. The cost for the paper campaign, they're investing $375,000 per year. And the cost for the mass marketing campaign, they're investing $325,000 a year. These are they're essentially total marketing budget. And so if we add them all together, we have a total marketing budget of $850,000 a year for this particular company. The business is currently assuming that the more dollars they give to the department, the more customers the department's going to bring in. So essentially, if we look at the table of customers, we're assuming that the customer from the digital campaign is going to have less than the paper campaign, which is going to have more than the marketing campaign. So we're assuming that the customers match the money. A table of customers is obtained by simply counting the different obtained by method. I love it. By simply counting how many customers are in each category. I see. Customers obtained by method. So how many customers did I obtain by the method of a digital campaign, by method of a paper campaign? I see. That's what I was saying there. Sorry. At the alpha equals 0.05 level, test if the number of customers matches the funding from each department proportionally. So here we have the number of customers brought in from digital, paper, and mass marketing, and we're trying to compare that to the costs. So note how this problem is different. I only have one categorical variable. Essentially, that is for each customer, which method were you brought in by, digital, paper, or marketing? So I go up to a customer, say digital, paper, or marketing. They say, oh, I came from a paper ad. I say, fantastic, I'm going to mark you as paper. And then I do that to a whole bunch of different people, and I count them all up, and I put them in this table at the bottom. The question is, do the proportions in this table at the bottom match the proportions of money that we've been spending? So I'm going to be doing a calculation, converting the proportion of money to a percentage, and then converting that to a count below. All right, well, let's take a step back and start with the hypotheses. In general, we can write them below. Again, we can get more specific if we want to, depending on the null and alternative hypothesis. But broadly speaking, it's the population values follow the specified distribution, whether that's uniform, whether that's the distribution of the marketing budget, whether that's whatever. So whatever the specified distribution is, that's our null hypothesis. And the alternative is that the values don't follow the specified distribution. As with all of our statistical testing, and I know I've beat it like a dead horse over the course of the semester, but remember, these tests don't relate to the people we observe. What these tests are doing is using those that we observed to make conclusions about everyone that they represent, even or especially people that we didn't observe. All right, so we already have the contingency table, the observed values. What we have to do right now is turn what they expect into the distribution. So remember, what they expect is that it's going to match the amount of money that was spent. So we have money spent in each department. The total budget is $850,000. And what we're going to do is find what percent of the budget was put in each of the marketing categories. To do this, we divide each campaign's budget by the total budget to get the percentage. So for the digital, we had $150,000. We divide that by the total budget, $850,000, and get 17.6% of the budget is going to digital. And because of this, we'd expect 17.6% of the customers to be brought in due to digital. Same thing with paper, $375,000 budget over the $850,000 total budget, and we get 44.1% of our budget is going to paper marketing. Same thing with mass marketing, and we get 38.2% of our budget is going to mass marketing. You'll note that I'm writing the percentage values, though these actual ratios come out in their decimal forms. Now that I have the expected percentages, I can find the expected counts, and it's important to realize that the equation for observed minus expected squared, that divided by expected, the chi-squared test statistic equation, requires the expected counts, not the expected percentages. So to get from the percentages to the counts, we multiply the sample size by the decimal form, or the proportion, for each of the categories. So the decimal form for the digital was 17.6%, the decimal form 0.176. I multiply that by my sample size. That is the total number of people I talked to. So I add up all of the people from that observed table. Add up all the people from that observed table. I get 303 from the total number of people in the observed table. And from that, I get 53.47. For paper, I have 133.68. And for mass marketing, I take the percentage in decimal form, multiply by 303, and get 115.85. So my contingency table of the expected counts, I just put each of these in the table. I get 53.47 for digital, 133.68 for paper, and 115.85 for mass marketing. And now I'm ready to go and calculate my test statistic. So it's worth mentioning that sometimes The percentages or proportions are given directly, and all I have to do is the step on this slide. That is, I'm not given something like X amount of $1,000 in a marketing budget. I'm just given, hey, I expect Group A to be 18.3% and Group B to be 12.2%, and that's just fine. You can do that. Or I expect them all to be even, and again, in that case, we take the total number of groups and do 100 divided by that to calculate the percent that we would expect to be in each group. So sometimes you can just skip to this slide and you don't have to do the stuff on the previous slide to find these expected values. But again, just like with the test of independence, once I have my observed table and my expected table, I can find the difference between them, square it, and then divide by the expected. Ultimately, when I do this for my 3 cells and add up the results, I get 35.586. Calculating the critical value based on the rows and columns, and again, for my columns, I have 1 row, I have 3 minus 1 columns, so my degrees of freedom are just 3 minus 1, or 2. I'm doing, it looks like an alpha of 0.05, that's fine. Degrees of freedom of 2, and again, I'm putting the area in the top tail. My cutoff is 5.9914. Because my test statistic is greater than my critical value, we reject the null hypothesis. That is to say, our number of clients that we're getting in based on our campaigns does not fit with the proportion of the budget that's going to each of the campaigns. All right, now it's time for your turn. You get to try one of these out. We're going to see if the appearance of real-life Pokemon changed the number of registered voters. I love it. I love it. You know what? Pokemon just seem to appear everywhere you go. I don't know how that happens. We can see one peeking out down there. In any case, go on, pause the video, give this one a shot. See if you can do your chi-squared goodness of fit test, and then we'll check in a moment. All right, coming back to it, let's see. So the expected percentage for each cell, well, we expected it to be uniform, the same percentage in each cell. So we had 3 cells, 100 total percent. So we're expecting 33.3% in each cell. So don't worry about this. If you said all the groups had the same and then all the groups are different, that's just fine. I'm just writing this a different way so you can see a different way. The proportions in each group are the same proportion. That's the null hypothesis. And the alternative is that at least one of the proportions doesn't match that. Again, you can't just write that they all are not equal to here because it only takes one of them to be different, just like with ANOVA. All right, total sample size. Well, I add up the total number of observations from each of the 3 cells in the observed contingency table, and I get 941 total observations. The expected count for each cell is the decimal version, the proportion expected for each cell, times the total sample size. So for each cell, I'm expecting, because they're all the same proportion, 313.67 participants in each cell. That's the expected value, assuming these were all the same. And essentially all that is taking the total number of people and evenly splitting them in the same cell. So that's where we get these numbers here from. From here, we have the observed and expected. We calculate this. I got 2.5143. Hopefully you did too. For the critical value, this was actually the same critical value as the one I just did. But if you calculate it yourself, hopefully you got the same thing. 3 columns, so 3 minus 1 is 2 degrees of freedom. Chi-squared 0.05, and again the 0.05 is in the upper tail. So we get 5.9915 as our cutoff. Because the test statistic is not bigger than the cutoff, we fail to reject the null hypothesis. There's not enough evidence to reject the null. And actually, I write test statistic is greater than the confidence or the critical value. That's not true. The test statistic isn't greater than confidence value. And that's why we fail to reject the null hypothesis. So not enough evidence here to determine that the voting pattern changed. All right, ladies and gents, well, that takes us to the end of our chi-squared tests lecture. set. So we talked about the test of independence. And of course, in this video, we talked about the goodness of fit test. So we talked about the conditions by which we do it. It's really analogous to the one sample test. We kind of null hypothesize a distribution and see if our categorical values fit that distribution, yes or no. And through this, we got to play around with creating the expected values from a couple of different scenarios, got to try out a couple of different problems together, and then see how we calculate the test statistic and do these comparisons. Well, this is the end of our lecture set. Don't forget to check out the software videos on how you can do these analyses in software. So thanks for sticking with me through this video, and I'll look forward to catching you in the next one.